Good evening and welcome everybody. This is Obi-Wan Pez for Simplex Pachinko. We are going to be looking at some more Calc 2 subjects. Again, this is kind of my first draft of what I'm going to be doing during class this semester, and get into anything that people request if anybody stops on by. So, feel free, if you are one of those people who has questions, stop on by now or in a future stream. I will always be doing Wednesday nights unless something important comes up. Or if I decide to take a vacation, whatever. So Wednesday nights are going to be my nights I'm pretty much always going to be here. Monday mornings I've been trying to get off the ground, but lately it's just not working. So maybe, maybe not. We'll see how it goes. And again, gaming streams on Friday nights. Lately we have been getting back into Control because Control is a pretty awesome game. I did lose access to my Xbox, unfortunately, so, or rather, it's very slow. So I've been catching the PC version back up to where I was, and I'm pretty close. In terms of calculus, we had been talking about... Okay. Now, you know what? This is not... Alright, whatever. This is not quite where we were before, but whatever. Window's been resized a bit. Alright, so for tonight, we're going to be talking about improper integrals. That's pretty ugly. Yeah. Oh, you know what? That's why. We're just really far zoomed out. That just looks weird. Alright, let's try this again. Alright, so integrals are called improper if we're starting to look at questionable things that are going on with all of our integration. So, for instance, one example of that might be... Why is that changing color? That's slightly alarming. Well, it's still coming through, and it's still coming through here, so okay. We'll just go with it. So one of the things that, for instance, we've been told you can't do that is anytime that you have an integral that involves some sort of infinite object, whatever it might be. So, for instance, if we were to have a function y equals 1 over x, and if we wanted to integrate this 1 over x dx from, for instance, 0 to 1, or from, let's say, 1 to infinity, or any sort of other stuff that could be going on here, we're going to end up with problems due to the fact that when we take the integral of these things, we end up with logarithms, and then when we're trying to do log of 0, that, that creates a bit of an issue, and also log of infinity. What exactly are we supposed to do with these things? So, improper integrals offers us a solution for this, basically whereby you just take whatever you didn't like about this stuff and you could just replace it with a variable, at least temporarily. So we take integral from a to b of f of x dx, where f has a discontinuity at some c inside of a to b. Could be the endpoints, that's okay, like we did here. That's perfectly fine. Or if a or b are infinite. All right, in either of these cases, we're also going to end up with same stuff. So there is an issue here if we end up with infinite values, or some number c within a to b is discontinuous. So what we can do with this is we say, okay, we'll take the integral of f of x dx, and we get capital F of x, normally plus c, but again, here we're using a definite integral, so we can kind of ignore that. Okay, so when the integral of f of x dx is capital F of x plus c, then we end up with the integral from a to c of f of x dx plus the integral from c to b f of x dx Then here we're going to end up with capital F of c minus capital F at a, plus over here capital F at b minus capital F at c. And then with these, we have to take into account the fact that, again, we don't know exactly what capital F at c is. It's discontinuous from above, so what we're going to have to do is say that this is going to be the limit as x approaches c, capital F of x minus f at a plus f at b minus the limit x approaches c of capital F of x. Now keep in mind, right, these limits might not be the same exact thing. So if we have a discontinuous object that looks like this, then we're going to have two separate limits, and that could create some interesting differences within all of this. So maybe these are one-sided limits, really, is what we're going to be looking at. So this is C and A, so we're coming from the negative side here, and we're coming from the positive side on this one. And with those being, again, separate limits, they could potentially have different values. appears to have crashed. Hang on one sec. Yep, I appear to have broken pretzel rocks. So, we may not have any more music for the time being, but that's alright. Oh, cool. I updated my headphone software, and it needs to be restarted, or the whole computer needs to be restarted before I can use that again. So there's a possibility that Pretzel Rocks is somehow tied to that. Huh. Oh well. Or I could just restart it and it works fine. Alright, cool. When in doubt. Alright, so in the case of A or B being infinite values, we're basically going to do the same thing. We're going to take the limit as x goes to some value c, or we could just call it a or b depending on what it is, instead of actually writing an infinity symbol, because technically you're not supposed to write an infinity symbol in the middle of a calculation. That is, as it says above, improper. So, improper. So in the case of something like this example here, we could have that the integral as we go from 1 to infinity of 1 over x dx is then equal to the natural log of x as we go from 1 to, we'll just call it b, and then have to take the limit as b approaches infinity. So when we look at this, this is saying that we're going to do the limit as b approaches infinity of the natural log of b minus the natural log of 1. Natural log of 1 is 0. And so we are just left with this limit. Now the thing is that as as b goes off to infinity, the natural log also continues to rise forever. It will never reach a particular value. So because of that, this whole thing is going to have an infinite value itself. So the integral will end up being an infinite value. We have an infinite area underneath that particular curve. Alright, some more interesting examples might be something like integral of, as we go from 1 to infinity, of 1 over x squared dx. Which, as we look at this, this is going to be a well, it's a negative 2, so we need a negative to be brought out, or we can use that as part of our power rule. Right, so we have a negative 2. We want to increase the value of our exponent. It's going to become negative 1, so that's 1 over x. And again, plus c, but it's a definite integral, so we can ignore that. And then we go from 1 to b, the endpoint again. And again, we have to move all this over here. Take the limit as b approaches infinity of negative 1 over x. This is going to be equal to a limit as b goes to infinity of negative 1 over b minus a negative 1 over 1, which is the limit as b approaches infinity of negative 1 over b plus 1. And what we have here is that b is going to approach infinity. That's negative 1 over something very large. This whole thing here will just become 0. And then plus 1. So the area for 1 over x squared dx, or the area under the curve 1 over x squared, from 1 to infinity is just going to be 1. We could do this with all sorts of individual problems. All right, you don't have to necessarily use a constant, but it needs to be constant with relation to the variable that's in use. So for instance, if you're using your limit of integration here as we're going off to infinity, you could call it t instead of b. Just call it like a different variable, that's fine too. All right. This is one of the integrals that I absolutely hate, so let's do it. Seems interesting when I say that, I'm sure. When we look at something like the integral from 1 to infinity of 1 over x natural log x dx, this always ends up being something very interesting. You look at it and you can't actually do anything with the integral just by itself as it sits right now. However, one of the things you can do is do a u substitution. So if we think about this and say, all right, which function do we have just a function of, and then what is its derivative? So there are kind of two functions here. We have the overall functions 1 over x and 1 over natural log of x. And if we just look at them in whatever place they're in, we have what looks like x and a natural log of x. These are our two separate functions. So these in-place functions are going to become our u's, and the overalls can become du's. So if we look at the combination of any one of these, no, it doesn't necessarily always have to be like this. It could be that one of our overalls could be a u, and one of the in places could be a du. It's not very likely though. So this is just kind of like how I'm typically looking at it. If you notice this combination here, what we've got is one of the overall here can be 1 over x times dx, and a function that's just kind of randomly stuck in there is natural log of x. 1 over natural log of x, if we look at this, there's not really a whole lot we can do with it. You know, whether it's in yep, whether it is 1 over natural log of x, or if it is like the du that we're supposed to get, like I don't know any particular integrals that are going to yield this, nor do I know the integral of this thing. So that's really not helpful. Therefore, if we look at the other one, right, 1 over x, I know that the integral of 1 over x is going to be a natural log. I know that the derivative of 1 over x is going to be negative 1 over x squared. Do I have either of those things? Right, I have a natural log. It's just that it's in the bottom. So what do we do to deal with this? Well, we let, in this particular case, u be equal to the natural log of x. We let du, that's off the page. Might as well. Let du equal 1 over x dx. And now I've got a pair, right? This actually is here in this function. So 1 over x dx is going to become du. Natural log of x is just going to become u. It's in the bottom. So this is now 1 over u du. We're taking the integral as x goes from 1 to infinity. This is a really important distinction that you make, by the way, that x has these limits and u does not. So the other option is that you change the limits and you say, okay, what are the limits of integration going to be if we let 1 go into these places? So if 1 is put into natural log of x, we get a 0 back. So you could, in fact, write this as u equals 0, 1 over u du. And then we get an infinite value into a natural log of x, which is going to be an infinite value. So u is going to go from 0 to infinity, whereas x is going to go from 1 to infinity. If you do choose x as your limits of integration that are going to stay there the whole time, you need to remember to convert back. If you are going to use u, you don't actually have to convert back. You can just leave it as the integral that you're going to find here. So u equals 0 to infinity of, we already know what this integral is, right? Du over u, or 1 over u du, is going to end up being the natural log of u and u is going to go from 0 to infinity. We get a bit of a problem here in that you can't plug in u into a natural log. Alright, sorry, you can't plug 0 into a natural log. And then up here we're going to get an infinite value, so that's not really helpful either. Take the limit as u goes to infinity. No, sorry, not u. Again, you can use t, or you can use something else, not x, not u. So I guess b goes to infinity. We'll just use a and b as the limits of integration because that makes it easier. Of the natural log of b minus limit as a goes to 0 of natural log of a. This also creates a bit of an issue. Actually, no, it doesn't. We good? Alright, if we were to evaluate this, b is going to infinity, the natural log of b is going to be infinity. This is then going to be a minus natural log of a, when a is going to 0, is going to get us a negative infinity here. So this is going to get us infinity plus infinity, which is going to just be an infinite value. Yep. Alright, so this is how that works. We could, again, instead of using u, we could have used this with x instead. You do the same integration, you still end up with the natural log of u, where, but this time we say that x is going from 1 to infinity, and then here you say, well, if x is 1, here we have to trade this back out. This is the natural log of x. Evaluated, x goes from 1 to infinity. Either way, this ends up being the same stuff. Due to the fact that the final limit of integration is going off to infinity, right? So our b is going off to infinity, and our a value is going to 1 inside this double natural log. So the natural log of 1. Natural log of 1 is 0, and now we've got the natural log of 0, which is undefined, negative, approaching negative infinity. So then you have to plug in the proper values to make sure that that all works. Right. So one of the other applications that comes about in differential equations, which we have talked about on this channel before, are called Laplace transforms. Now, there are many different types of transformations that you can do with integrals. Integral transformations have been studied for a couple hundred years anyway, and have been found to cause certain integrals which we thought were impossible are actually not that bad once you do this weird transformation thing. It isn't always weird, but many times it is. So Laplace transforms in particular are usually written as this cursive L of f of t is going to be equal to the integral from 0 to infinity of f of t times e to the negative ts, I think, right? Or st. Doesn't really matter there. Where s is just some constant, but then we evaluate this on, of course, negative st f of t dt. Yeah. Which is going to give us a capital F of s. So the individual functions that we get for this kind of stuff really are not that much fun depending on what you're doing. Most of the time they require integration by parts. Many of the times it gets really ugly and really nasty when you're trying to do these kinds of integrals. There we go. So for instance, the Laplace transform of just t is going to be the integral from 0 to infinity of t times e to the negative st dt, which again, we're going to be doing integration by parts on this. You can't do u substitutions or anything like that. It's just not going to work. So here we let u be equal to t, and therefore du equals dt. dv is going to be equal to e to the negative st dt. So therefore v is going to be equal to, you take this integral, take the integral of this thing, s is a constant, so this is going to be a negative 1 over s, gets knocked out front, and then you've got e to the negative st. When doing integration by parts, again, this is uv, so u is just t, v is this thing, so negative 1 over s times t, e to the negative st is uv, minus integral of v du. So v is a negative 1 over s e to the negative st times du is just dt. And then do this integral, which looks oddly familiar, doesn't it? This is going to be a negative 1 over s t e to the negative st evaluated from 0 to infinity. And this is a positive 1 over s times the integral of e to the negative st dt, which we already did on the step above. The integral itself is just going to be the thing we found, well, the v that we found earlier. So this is going to be a negative 1 over s t e to negative st evaluated from 0 to infinity. Again, t equals plus 1 over s times a negative 1 over s e to the negative st evaluated from 0 to infinity. So what's that going to be? Well, you can plug in infinity into all of these individual pieces. Again, we can't technically do it, but you just say that, okay, I'm going to take the limit as b goes to infinity of negative 1 over s times b e to the negative sb. All right, in this particular case, you have to look at what's known as the hierarchy of functions and say, well, which one's going to happen faster? Is b going to go into, is a linear b, this term here, going to go off to infinity Or is e to the negative sb, is this b going to cause the e to do something faster? And the answer is, well, of course, exponentials pretty much always win. So certainly over a linear function. So here when we plug in larger and larger numbers for b, having an e to the negative sb is going to get us smaller and smaller and smaller values. It's going to tail off as we continue on further. So here, this is going to just end up being 0. All right, then we subtract this thing evaluated with 0. So now this is going to be a minus a negative is a plus. 1 over s times 0, e to the 0. All right, well, that's easy. This whole thing is now just going to be 0. Plus. Oh, nope. Minus. All right, we end up with this piece here. We have 1 over s times a negative 1 over s is a negative 1 over s squared. E to the negative st, evaluated from 0 to infinity, which is, again, going to be negative plug-in All right, so a minus 1 over s squared e to the negative s, and again, this is going to end up being b, so we want the, screwed that up, didn't I? Not a big deal, just kind of forgot to put the limit in there. B goes to infinity of 1 over s squared e to the negative sb, and then we're going to, again, subtract, which makes this a positive. We're going to plug in 0 for t. This makes 1 over s squared e to the negative, well, again, that's just 0, e to the 0. E to the 0 is just 1. And this time we don't have a term out in front that's causing it to be 0. We don't have a t. We just have this constant, 1 over s squared. All right, so again, exponential is running towards 0 in this particular case. As b goes to infinity, e to the negative sb is going to become e to the negative infinity. Well, e to the negative infinity, again, causes this to go off to 0. So 0 minus 0 is still 0. 0 plus 1 over s squared is just going to be 1 over s squared. So f of s for the original function, Laplace of t, is going to be 1 over s squared. All right, there's a whole table of these things in your differential equations book, those of you who have one. And if you don't worry, it's coming. All right, so that is a Laplace transform. It is a specific use version of an integral transform. So basically what we're doing is we're taking the integral, usually from 0 to infinity, of some function times what's called a kernel. So this little e to the negative st is the kernel of the particular transformation we're talking about. So generally speaking, this is an integral from 0 to infinity of f of t times some kernel, which is a function of s, dt. Now it is also possible that the kernel has a t in it, so we can actually change this a little bit and say it's s comma t dt like that. All right, something else that they want to do in the book is to compare two different types of integrals. So for instance, taking the integral from 1 to infinity of a function dx over square root of x plus 1 isn't actually possible to take this integral. So we would need some sort of dx term up top to be able to compare it. And we're only off by a half of an exponent instead of one full exponent. So that's unfortunate. What we can do is, instead of actually taking this, we're going to compare taking the integral from 1 to infinity of dx over square root of x. Adding 1 on the outside here is just going to increase the denominator and actually make the whole function just a little bit smaller. So here what we get is that we're actually looking at a function which is slightly larger than the original one that we wanted here. And if we look at this, this is going to get us let's see, that's going to be a 1 over positive a half. Because we had an x to the negative 1/2, we're going to increase that value by 1, and it's going to end up being positive 1/2. So 1 over 1/2 times just the square root of x. Evaluated from 1 to infinity. Here we get a 2 square root of x evaluated from 1 to infinity, and then we can alter this again so that we get the limit as b goes to infinity of 2 square roots of b minus 2 square root 1, which in this case, right, square root of 1 is just 1. We get minus 2 at the end. And then here, this is going to be limit b goes to infinity of 2 square roots of b. Since we're taking the square root of something that's going off to infinity, we're still going to get something infinite in extent. So this is still going to be infinity, minus 2 is just going to be infinity. So this will diverge. However, this thing here is smaller than the original. How much smaller? Well, not by a whole lot, because the denominator is just going to be plus 1. However, we can't actually prove that the original one here will converge or diverge. We just know that it could diverge because our comparison integral ended up diverging. So because the comparison integral diverged, the function underneath it could diverge or it could converge. We don't know. So in order to obviate that, we have to, or in order to fix the fact that we have multiple answers here, or multiple potentialities, we haven't eliminated any, we have to change the comparison integral. right? Since this integral diverges, it is going to be inconclusive to tell us what's going to happen with the original. So we have to figure out something else that is better. And in this particular case, if we can find a function that will get, instead of over the top of dx over square root of x plus 1, if we can get something that is underneath it, which then also diverges, then that proves that the thing above it must diverge, right? If something underneath a particular function, like down here, says that it will diverge, then it is not possible for something that is always above it to be able to converge. There's no possible way. So in this case, what's going to be easy that we can do to find something out? Actually, I didn't need to cross all this out. We could have taken the integral of 1, or from 1 to infinity, of dx over 2 square roots of x. 1 over 2 square roots of x will always be smaller than 1 over root x plus 1, at least from 1 to infinity. Right, so for all values that we're going to get, this ends up just being the exact same integral, but it's half of what we found. So I didn't really need to cross all this stuff out. So we would get the limit as b goes to infinity of the square root of b minus 1. Which, yet again, the limit as b goes to infinity of the square root of b is still infinity, and then we subtract 1, so it's still infinity. So in this particular case, this still diverges. However, coupled with this fact that we found earlier, allows us to say that since something that is always below it diverges, then the integral from 1 to infinity of dx over square root of x plus 1 will also diverge. It's a fun little puzzle to try and figure this stuff out. next section starts looking into all of the individual series tests for Calc 2. Be honest with you, I don't want to do them tonight. I kind of want to just do some like random stuff. But at the same time, I don't know if that's going to yield any results whatsoever. So it's like, I don't want to scare away all of the people who are here for video on demand. See you out there. Thank you. I mean, I was just sort of talking about it. So. Oops. All right. Something more my speed for tonight, because I don't know. I'm just not feeling like I want to do the other one. So in Calc 1, let's do substitution for integrals. So we had something, well, I mean, we could do just about anything, but in the case of substitution for integrals, we can throw in pretty much anything we want here. So take the integral of x times the quantity 1 minus x raised to the 56th power dx. So for this, naturally, just looking at it, you'd be like, well, I can't do that because we got multiple pieces that are not really communicating terribly well. If we let the inside of this be u, then du would be the derivative of 1 minus x, which would just be negative dx. Now, unfortunately, we do have this other x that's out here, so that isn't being included in all of this stuff. It's going to be much harder to try to figure out what exactly is going on here. You could let that be, solve it for this. So x would end up being equal to 1 minus u. And in theory, you could start trying to combine that, but it's going to get complicated. So instead, one of the things that you can do is, instead of doing a u substitution like that, we can split this up. And say that since we're multiplying here... Wow, I just did that, didn't I? Okay, nope, never mind. Let u equal 1 minus x. Yeah, I tried to like give each of those pieces a 56th power. That does not work. All right. Yeah, and instead of multiplying this all out, as much as I do love Pascal's triangle, this is going to be a nightmare to try to do with the 56th degree. You're going to have 57 terms going across. So, yeah, let's not do that. On the other hand, if we let u be equal to 1 minus x, then x is equal to, if we flip this around, 1 minus u. We'll use that here and use that here. So what we've got is the integral of parentheses 1 minus u times u to the 56th power du. Because, again, dx is just du. Oh, no, negative. So now what we can do is just take this u to the 56th power and multiply it through to 1 and the negative u that are already there. So it's negative integral of u to the 56th minus u to the 57th du. And then we get this negative, so we can multiply that in. Get the integral of u to the 57th minus u to the 56th du. All right, then we want to take the integral. This is just a simple power rule, so we're going to take the integral of a power. It's going to increase the power to 58. And then we're also going to need from looking at the power rule, we're going to need a 58 out front that we are going to bring up into the exponent. So there was a 58 here. But that also means that we need a 58 on the bottom in order to counterbalance. Okay, minus u raised to the 57th power for the same reason. We're increasing the exponent by 1 and divide by 57. Plus c. Then what we can do is go back to the original and say u is equal to 1 minus x. So this is going to be 1 minus x raised to the 58th power divided by 58 minus parentheses 1 minus x to the 57th power divided by 57 plus c. That is the integral of x times 1 minus x raised to the 56th power dx. All right, one example of like a different kind that we might find here is the integral of cosine raised to the third of theta d theta. By itself, it doesn't look too bad. You might think, oh, it's a power rule. Great. What is the u function that you're going to pick? If your u function was just cosine of theta d theta, then what's du? Well, that's going to cause us to have a bit of a problem here. Because again, we don't have the other piece that should be here, that normally is here. So instead, what we can do is we can split this out into the integral of the cosine squared of theta d theta. Well, not yet. Cosine squared times cosine of theta d theta. And again, it would be really nice if we could use these cosines in some way. Again, looking at this in terms of our function, if we have a cosine function somewhere, its derivative should be a sine function. But luckily we can go the other way. If cosine is the du function, then the u function has to be a sine. Well, how do we get cosine squared to be something with sines? All right, it's going to be cosine squared of theta is equal to 1 minus sine squared of theta. And then multiplied through by the cosine of theta d theta. You get the integral of the cosine of theta d theta minus integral of sine squared theta cosine theta d theta. Let u be the sine of theta. So du is going to be equal to the cosine of theta d theta. We have cosine of theta d theta exactly, so that's just du. And then here we let u be equal to the sine of theta. So here this is the sine squared of theta. This is u squared. All right, and this stuff is actually doable. So what is the integral of the cosine of theta d theta? That is going to be the sine of theta. Plus c will wrap up all the way at the end. Here we've got a minus integral of u squared du is going to again be 1/3 u to the third and then plus c at the end. So we can get a sine of theta minus 1/3. U is again the sine of theta, and we're cubing it. So sine cubed of theta plus c. And if you can't remember what you were doing, maybe write that all over again. let's try this. Getting that this is probably not impossible, but not particularly nice. So integral of sine squared theta minus 2 sine of theta times sine cubed theta minus 3 sine squared of theta parentheses cubed cosine of theta d theta. Alright, so with this there are a few things that we can do. We can try to combine as many like terms as we have. We can try to multiply this stuff, all of the sines stuff out, leave the cosine of theta here, and don't try to change any of these sines to cosines. It would be really good if we could just multiply by cosine of theta d theta to everything and then be done with it. Right? We would not need would not need any other du terms. So this is going to be, I might suggest multiplying this out as best you can. At the moment, just leave this. So this is going to be the sine squared theta minus 2 sine of theta, parentheses. No. That's what I forgot. Alright, so we can factor out a sine of theta from both of these two terms. We're left with a sine of theta minus 2. This stuff here has two sines in common. So if you want to take out a sine squared, and then here you have to cube it. Since it's multiplied, this is actually a perfect opportunity to use this. So take out sine squared from both terms, and then cube it. So sine squared cubed is going to be sine to the 6th of theta times the quantity. Here we just have one sine of theta left over. And then we have 3. That's it. Just 3. Cubed. And again, cosine theta d theta. Here these two terms can combine. Here, might have to actually just multiply everything out. As much as I hate it. All right. So here we have sine of theta minus 3 all cubed. If we basically we're just using Pascal's triangle on this. This is not surprising. You all know I love it. Here we have the sine cubed of theta minus one of these and two of those is going to get us a minus 3 sine squared theta times 3, 4 being the position. All right, in Pascal's triangle, this is 1, 3, 3, 1. So if you have mixed cases in the middle, these are going to end up doing something to the constants here. All right, 2 3's is going to be 9 multiplied together. 1 sine, and then here we have a 3 from the natural 3 from the Pascal's pattern. All right, so 1, 3, 3, 1. Here, because we have 2 negative 3's, that's going to be squared, so it's going to be positive 9 times sine of theta times the 3 that was already here, so that's 27 sine of theta. And then if we cube negative 3, that's going to be a negative 27 cosine theta d theta. All right, so integral sine of the 7th of theta times, this is where it gets a little interesting. We're going to have here sine to the 4th. This is going to be sine to the 3rd, and this is going to be sine to the 3rd. So this is going to be a minus 2 and a minus 9, a minus 11. Nope. All right, now squared is going to be negative 2 times the negative 9 is positive 18 sine squared, and a sine times the sine here is also going to be sine squared. So that's 18 and 27 is going to be 45 sine squared theta. Hey, Kiwi Gamer Romania. How's it going? And then we're going to multiply through again to get singles. So here, negative 2 times positive 27 sine. It's going to be a negative 54 sine of theta. And that's going to be a negative 27 on top of that. So that's going to be negative 3 27s. So 81. And then we also have a negative 2 times a negative 27 is going to be positive 54. All right, take all that, multiply by the cosine of theta d theta. All right, well, glad to hear you're doing all right. Anything going on that's interesting out in the world? Whether yours or somebody else's, that's fine. Here, raised to the 7th power, or sine to the 7th power, is going to get us sine of, nope, sine raised to the 11th power of theta. Jeez, man, come on. Of theta minus 11 sine to the 10th of theta plus 45 sine to the 9th of theta minus 81 sine to the 8th of theta plus 54 sine to the 7th of theta, all times cosine theta d theta. This just means that this is going to be yet another polynomial. trying to finish the entire Romanian high school math curriculum needed for final exam. Hardest program in under a month. So I can finally start university stuff without missing a single prerequisite. Yeah. I can imagine. That's a bit of pressure. So, bit busy. I certainly do not blame you one bit for going on vacation. At least for a little bit. Yep. Trying to do the entire high school 4-year math curriculum in a month. Yep. Yep. It's pretty intense. I mean, technically it's 1/48th, but like, would you actually be in school the whole time? Or, of course, I also don't know how, right, I don't know how your country does it. So, in the United States, we get the summers off, so that's why. I mean, that's one reason I'm here. Uh, no, no, no. It's still insanely hard. Alright, we can let u be equal to the sine of theta du equals cosine theta d theta. We have that here. It's du. And then going all the way across, just the sine of theta is u, so this is going to be u to the 11th. That's 11. U to the 10th plus 45. U to the 9th minus 81. U to the 8th. That's 54. U to the 7th. Yeah, normal pace. A year and a half a year would be good enough to slow down, calm, chill, succeed. Have too many interests in math and science. Only way to satisfy a portion of them is to start as early as now. Yeah, that's fair. As insane as it definitely feels, I'm sure. All right, take the integral here. We're going to get 1/12 of u to the 12th. Here, this 11 actually comes up and becomes part of the next exponent up. In fact, it becomes the entire next exponent up, so this is minus u to the 11th. All right, 45th, we want to take a 10 up. So you could either say that this is 45 over 10 or 9 over 20. Wait. Hang on. No, 45 over 10, which is 4.5, which is 9 over 2. Okay, much better. U to the 10th minus, this is going to become a 9, so we're going to take a 9 out of 81. We're left with 9. Negative 9 u to the 9th plus, we need to take an 8 out of 54. Well, we can take a 2 out anyway. So 27 fourths u to the 8th plus c. Oops, wait. I can't do that yet. Then we got to plug the sine of theta back in. Sine 12th of theta divided by 12 minus sine the 11th of theta over, nope. Just minus that sign. plus 9 halves assigned to the 10th theta minus 9 assigned to the 9th of theta plus 27 fourths assigned to the 8th of theta plus c. Okay. Improper integral should not be on the high school curriculum unless y'all are doing Calc 2, which, you know, probably not. Yeah, so this actually is Calc 1 type stuff, but I picked, like, I did an easier problem up here. Oops. Ah. Not that. Yeah, I did an easier problem here. Where I said, let's have integral of cosine to the third of theta d theta. And the way to do this really is to split this up into two functions, a cosine squared and a cosine, and then say, well, if we want a function and its derivative, cosine and cosine isn't going to work, but we can translate a cosine squared into a sine squared. And so trade that out, doing normal trig stuff. When we multiply all this stuff out, then we got one straightforward integral and one that we had to do a u substitution on, which then allows us to get this thing, which then allows us to plug in this other stuff down at the bottom. Yeah, this one was okay too. Similar type thing. Having the 1 minus x inside this really high power was really inconvenient. So what we did was we said, okay, let's switch and have just plain old u be 1 minus x. So here this is just u to the 56th power, and then x could be translated to 1 minus u, which then allows us to multiply this stuff together, again, very simply, which then allows us to take integrals and get all this stuff. So, anyway. Alright, so, do you have any particular questions that you would like to cover? Because you have quite the exam coming up. Yeah, if there are any, you know, any particular areas that you're not 100% on. Didn't encounter anything hard. That's good. Means you're probably in a good shape. Fields and rings. Wow. That's pretty intense. That's abstract algebra. We don't actually cover that in the United States at all until, I mean, we talk a little bit about rings, like cyclic subgroups, when we talk about imaginary numbers or complex numbers, because when you raise I to a power, it creates a 4 cycle. We've talked about this before here. I don't remember if it was you or Matthew, but either way. Yeah, I have access to a bunch of AMATIC, which is the American Mathematical Association for two-year colleges, math exams from years past. And, you know, some of the stuff that they're always, always, always interested in doing, you know, the sum of 3 cubes is equal to the current year. They love doing that stuff. Now, there aren't necessarily going to be just the sum of 3 cubes which get the current year. We could, for instance, need to, for this particular year, make it the 4th power of 3 different numbers or 2 different numbers. Yeah, we studied a bunch of... So my spouse and I both took the same abstract algebra class, not with each other, but separately. I think with the same professor. Huh. It's been almost 20 years, so... Yeah, I got you. So, when I was given that one, you know, the a cubed plus b cubed plus c cubed equals 2021. I'm not even sure if this is going to work properly, but we can try. All right, so the sum of 3 positive integers being cubed but when used like that, it could be... Yeah. Anyway, so this was extremely... I didn't like the way that I saw this when I saw the answer for how this should be done. I was unsatisfied. No, it's not. This is not a standard formula. So what they said is if you go like this, and say C, let's let C be as high a number as we can possibly make it. So the cube root of 2021 it is 12.64. So we're going to say that 12 cubed is 1728. And then 11 cubed is 1331. Oh, right, yeah. And 10 cubed is 1,000. We'll do one more. So 9 cubed, 720. Yeah, 729. take the difference. So 2021 minus each of these things, going down the list. 1728. It's going to be 293. 1331 is 690. Minus 1,000 is 1,021. And 2021 minus 729 is going to be 1292. So then what you want to do is come up with the rest of the squares that could fill in the gap. So what is going to fill in the gap for 293, 690, 1021, 1292? If you get too low with C, so you start going like 8, 7, 6, then you're going to notice that C is no longer going to be the highest one. So take your pick. C will be greater than A or B. A and it doesn't matter. So I'm not sure that this one actually has a solution here, but again, I was just spitballing and saying like, well, this is kind of what you... Oh man, I've got a lot of magazines in here too. Yeah, sure, go for it. No, I got the American Mathematical Association for 2-year colleges because of the fact that I have paid dues for that professional organization. I get their quarterly magazine or something like that. Hmm. Oh. Square root of 5. All right. 2007 is divisible by 9. Just immediately right off the bat. We're left with a 200. 23. Plus 1 though. Yeah, might be able to do something with it. I'm wondering if this is possible for any 4 consecutive numbers, not just those 4 consecutive numbers. One of the ways that we could think about it is if you did n times n plus 1 times n plus 2 times n plus 3 plus 1. And say, is this a perfect square? It's no guarantee, obviously, but I'm wondering if that's that easy. So we're definitely getting n to the 4th. All right, if we do so we have to pick this one anyway. Let's see, so if we do 1, 2, and 3, okay, this is going to be just the sum of those three numbers. It's going to be 6 n to the 3rd plus the product of any 2 plus the other. It's going to be 6, 7. Wait, hang on. No, not plus the other. Product of any 2 in all three combinations. So 6 here, 3 there makes 9, 2 there makes 11. It's going to be 11n squared. Product of all three ends up just being 6n plus 1. Yep. That's symmetric. So because it's symmetric, this is going to be much easier. Oh, that was a mistake. I regret my life choices. Okay, close enough. I wanted to grab this one on this monitor. All right. Let's see. So 1, 6, 11, 6, 1. If we make this a negative 1, try this. This is going to make 1, 5, negative 5, 6, negative 6, 0, 0, 1. No, fail. Okay, so I'm going to go the other way with this. Without using a calculator, right? If I use a calculator, I can find the zeros for this function, no problem, and then say like, okay, it's going to be a perfect square or something. So, yeah. Instead, I'm going to use, what's his name? Descartes' formula, Descartes' rule of signs. So there are going to be no zeros in the positive direction because there are no sign changes in the function itself. In the so the rule of signs, it's not particularly like it's helpful, I guess, sometimes in this particular situation. For example, when you're forced to do something without a calculator. Yeah. So the number of sign changes of f of x I want this for later. You know what? I should not do that. Yields the max number of positive real zeros. Or reduced by evens. So if, for instance, we had like a positive to a negative to a positive, that would be two sign changes, which would mean that we either have 2 or 0 maximum positive real zeros. In this particular case, we have none. There are no possible positive real zeros because we have no sign changes between all the individual terms. It does have to be in order, right? So start with your highest degree in the polynomial and work your way down. The other option, I don't like that. Anyway, the other option is if you look at f of negative x, so the number of sign changes of f of negative x, in this particular case f of negative n, but whatever, it's fine. All the odd terms are going to switch their signs. So we get a positive to a negative, there's 1, to a positive is 2, to a negative is 3, to a positive is 4. There are 4 possible, or 2 possible, or 0 possible negative real zeros. And what I mean by reduced by evens is that let's say that you have a quartic polynomial like this, and we have zeros which are not positive real or negative real. Well, what else could they be? They could be complex, but complex zeros have to come in conjugate pairs. It's the only way for it to work. So if they're not in conjugate pairs, you know that there's a problem. Okay, so the only possible rational zeros are going to be the factors of the lead coefficient. Nope, sorry, the factors of the constant value divided by the factors of the lead coefficient, and it could be positive or negative. In this case, we know it's negative. Sorry, I don't know which question you're asking. If it's about the conjugate pairs, then if you're talking about this, the conjugate pairs that I was talking about, if a plus bi is a 0, then a minus bi must also be a 0. Alright, it's the only way for it to work. If you don't have that, then there's big bigger problem. If you don't understand that, let me know, because I can explain complex. Well, yeah, but that's beside the point. Oh, you know what? Yeah, I screwed something up. Because... oh no, I didn't. I'm good. Well, I don't want to be sitting here all night, so sure. Or give me a hint or something like that, and it'll be fine. No, yeah, okay. Mm. So because that's here, we've got 3n plus 2 minus 2. 1. I mean, if I'm like way off, let me know, but this is n squared plus 3n plus 2 parentheses squared minus 2 parentheses n squared. Yeah, okay. Plus 3n plus 2 plus 1. Yep, so x squared minus 2x plus 1 ends up being x minus 1 squared. So this is going to be n squared plus 3n plus 2 minus 1 parentheses squared. Yeah, okay. Well, I mean, they just want to make sure that you understand it. Of course, the problem that most countries have at this point is that it's just almost entirely like trying to slog, trying to get you through understanding how to just manipulate things, but that's not really... Yeah, I actually took real analysis and complex analysis as part of my applied math masters, so it's not... Um, I believe real and complex were, or else uh, real was and complex was an elective or something like that. But only for master's level. I think for me it was a senior level class, so 4th year. Or you could take it as your first year in masters. But yeah, we don't require it. Let's see. So yeah, we did not require it until either your senior year or first year in masters. Um, I'm not sure what the like difficulty is comparative, compare whatever comparatively. I would assume it's roughly the same, but who knows? They could make it a lot easier for like second year students instead of 4th year students, or you guys could just be doing a lot harder stuff. So also would not surprise me. Yeah, I really liked real analysis, even though it wasn't necessarily like, oh, this is something I'm using right away. It's at least given me an appreciation for what the uh, theoretical math majors had to go through, and a greater understanding of what it is we're actually talking about when we're talking about like taking limits and stuff like that. Nope, not that one. Well, topology is going to be a lot more useful, I think, in the future because we're going to have a lot more projects coming up soon that are going to require higher dimensional analysis, higher dimensional thinking, um, and even programming in 4, 5, 6 dimensions. Trying to do, for instance, data mining on something that can be potentially, you know, any number of dimensions that you want to start looking at, and then try to find patterns in that higher dimensional space. Like, it would be really useful to be able to say, I know how to manipulate things around Oh, right. Hmm. That is an interesting question. So it may also be different for your school. Um, our school has something that looks, roughly speaking, like Calc 1 goes to Calc 2, goes to all of your different stuff. So Calc 3, linear algebra, differential equations. Sorry. I think off to the side we have things that are like, oh, what did I call this? In my school is math proof. In my school now, what do we call it? This is, it's not abstract. It's a logic and reasoning course essentially, but it's for like math majors. Sometimes are discrete. Yeah. Our school calls it discrete structures. It's math proof. It's it's not discrete math. Discrete math is like a high school level course for people who are going to maybe do college level algebra, and that's about it. Discrete structures is like, mathematical logic, intense stuff like that. Doing actual mathematical proof, making sure you understand the structure, all that good stuff. Let's see. And then my school. Oh yeah, go for it. My school required pretty much anything above sophomore level. You had to take math proof. Um, and then there was actually a like calculus 4 way out here. And a senior level linear algebra. Differential equations, have your partial or nonlinear. It's like 2 separate classes, but you can do whatever you want with it. So you can convert everything to logical language. I don't. I have not done any like actual. See, I was a math education major, so after taking my sophomore level classes, I then had to do a few more in the like upper level stuff, but mostly it was it was like I started doing more education classes than I did math classes. My junior and senior years were just full of education classes. Real and complex analysis. Um, I did one called matrix theory that was out here. Oh, actually, I guess it would technically be off of the linear algebra group. Um, this was a Master's 1, at least in the US it is. Um, and a lot more of these three. Linear algebra, Calc 3, and differential equations are so interrelated. Um, in my differential equations class, I have to teach like the major concepts from both of these classes. So gets to be interesting. Calc 2 being a whole lot of like series sequences and integration, like numerical integration, things like that, that feeds into the rest of it. Uh, I did a combinatorics class, but I also did I didn't have to do matrix theory for it, but it was really helpful. Um, Neural networks. And I didn't have to take neural networks for it, but data mining made it a lot easier when I did neural networks and then I did data mining. Yeah, I mean this tier is basically what you're going to be asking about. Um, yeah. So my spouse took this one, topology here. She did it as a senior in college, so that was fun. The guy she had was pretty great, pretty mild mannered compared to a lot of the other people in the division or department. But and yeah, neural networks was fun. I would probably not be doing that here on this channel, but it's been a long time since I took it. I will say that there is a free book for neural networks. Granted, it's probably a little bit above your pay grade at the moment, but it's cool. Um, I'll link it here because why not? Is it that one? Does abstract algebra explain linear algebra? Um, Abstract algebra really tells you like why everything works, and um, the way that we did abstract involved a lot of like you need to now prove like why commutation works. Why are you allowed to do the commutative property? So prove that. Go on. It was kind of insane. I did a little bit of that when I talked about the Xena project. Um, so when I did the Xena project here, um, so really the thing is like, what do you know as of that point? Like, what are you allowed to prove commutation with? And part of it could potentially be like like you have left and right addition, and you also have um, the additive inverse property. So if you add on the left the additive inverse of whatever you had, then that takes it away. And then you can also add it to the well, add it to the right, but how does that work? So that's what I'm trying to do here. I don't remember. Anyway. Essentially. So it starts you over at nearly zero and says, like, here's what you know about math, then create the rest of the structures that exist. So you could, in fact, and this is what our linear algebra professor actually did. Both my spouse's original linear algebra 1 and our, because we took it together, linear algebra 2 professor. He was nuts. He created his own notation, and everything was uh, everything was completely different than what the standard notation is because he was trying to make a point about it. And I didn't get it because I was 22 and what do I care? I just want to like figure this stuff out and move on, which really was not a good attitude for me to have, but I didn't really get out of that attitude for quite a while. Going now, if I went back now, it'd be a lot better. More annoying real analysis. Yeah, somewhat. So abstract, we did as junior level, and real analysis was senior level. So, like, abstract algebra was breaking it down and saying, why are you allowed to do any of this stuff at all? Linear algebra was like, what are the symbols we're using a y? It's also senior level. Real analysis was, okay, what are the rigorous definitions of all this stuff? So you want to do a two-dimensional limit? Cool. You have a point, you have a distance. Within this area, you know, if you're trying to find a limit, then you're saying, like, within this small, arbitrarily small section, you know, this rule will exist. And then why does that work? Explain. Complex analysis was, like, really weird, because all that stuff went out the window. And complex analysis was like, okay, we're just going to get back to, like, doing calc, like calculus stuff. I mean, it's essentially calculus 4. But complex analysis was like, okay, we're going to take the integral of some weird thing that, like, you know, x, sine of x dx, and say, okay, this from 1 to 4. Is like, you know, going to do this. Nope. It's going to do this thing. I think, right? Yeah. So we want to find the area between, like, here and here. All right. How do you find the area between here and here? Well, there isn't a nice way to do this integral, at least not that I'm coming up with off the top of my head, but you never know. I could just be completely ignoring something obvious. So when you're taking the when you're taking this particular integral and trying to find the area under the curve, you might say, for instance, that, well, this doesn't make any sense as it stands. So what we're going to do is say, we're going to translate this via some sort of transformation into an integral. It's a residue. What's the notation for that? I don't even remember. But you're trying to find the residue of some stuff, which then basically ends up being like, do some calculations in complex numbers, and then this ends up becoming like, what is the area of a semicircle that is centered on this particular point? Let's say x equals 2 with a radius of 1. So this is going to be 1, this is going to be 3. So now we're just trying to find what's the area of a semicircle. And then, okay, that's 1/2 pi r squared. And, oh, look at that, we just found out that what this is. This is going to get us 1/2 times pi times the radius is 1. So that's it. It's pi over 2. Then you say, okay, now we need to transformation. Do the reverse transformation. So do the transformation, you get this residue, which is on complex numbers. Do this stuff, transform it back, and then you get a number that's like, I don't know, man, I'm not going to come up with anything useful, but like, you know, pi over 2 times some constant k times some value of, like, the stuff that's in between here. So like the sine of 4 or something like that. So you get like all this stuff, and it just dumps on the page, and you look at it and go, wow, that really cleaned everything up. Like, it just got me a number. It seemed insane the first time that I did this, because I was like, well, how did that work? That should not have worked. I have no idea what advanced calculus is necessarily going to be. Um, Me personally, I thought multivariate was basically starting all over again. Um, this is mostly numerical and integration methods. Linear algebras, matrices, differential equations, that's just differential equations. Okay, so it's probably doing analysis on calculus, just generally. Yeah, it seems reasonable. Starting with inequalities and sets to limits. Hmm. Yeah, so he's probably bringing in the like very rigorous definitions to calculus, whatever it may be. Yeah, oh, definitely. Um, Multimedia is going to be kind of the name of the game for the next 20 years. Uh, I mean, I'm going to essentially make my career out of that, I hope. Where I'm just going to be like trying to build up my library as big as possible so that I can teach students in a number of different ways. And I hope I can get there. Um, we'll see how it goes. All right. Yeah. It's going to be an interesting next couple of decades here. True. I'm not quite 40 yet, but nah, it's all good. I didn't think you were talking about me actually. Yeah, no, I got you. Right, you were talking about the math sorcerer. Anyway, um, yeah, I like trying to get as much information as possible from as many different sources as possible, so that I can have different perspectives on things, and that's one of the reasons why I like put out the call in this session for people to like tell me how you learn stuff, because I want to know if anything is different how it's different. Because, if it turns out that there's a completely different method across the world, um, that other people are learning, I would love to be able to take that and either try to teach it to my students or expressly not teach it to my students and be like, hey, so this is this is how this other one, or maybe give it to some like research students and be like, let's look at this and tell me why it works or doesn't work, either for you or for other students. And getting that information to as many people as possible is really kind of important. I, you know, I rail against politicians who are just like, oh, we need to, make sure that we preserve the. Ah, welcome to the fold. Yeah, I actually went the same route. That was my kind of second choice. I actually was offered a job at an insurance company to do fraud detection, and they were very interested in the fact that I had done neural networks in my master's. If I was doing that now, I would probably be making like twice as much as I am, but you know what? I like what I'm doing, and I'm not gonna. I'm probably not going to get replaced by a computer anytime soon. Yeah, also, right? If you're doing that on the side, you can always get extra money. Yeah, and trying to teach all of that is always an interesting and fun idea. I mean, learning how to teach something is also like a puzzle unto itself. So you try to figure out like how you can make this work for everybody or as many people as possible. And then the hard part is trying to reach the people who don't or aren't interested in physics, programming, or any of the math whatsoever. Um, that's fair. I'm sure your rank and file American math teachers probably look the same, um, in that they're like, I don't want to walk into this building every day and slog through, you know, hundreds of students who don't want to be here. Um, at some point, I was going to become one of them. So, I mean, that's why I left public schools and decided to go with. That's the other thing is that, like, teachers who typically do come onto Twitch, YouTube, whatever, even if they're not trained teachers or whatever, they're so excited about the subject and they want to be here and they want to like just spread the word. And the most motivated students are the ones who come. So, why are we so advanced? How do you mean? Oh, yeah. It has a lot to do with money. We oftentimes, and there's a great disparity between um, uh, different areas of the country, and just even no, you're not dumb. I mean, that's always the question, right? Is how can we effectively rank this in the first place? Is it I'd be interested to know if the exams that people are taking are like culturally biased toward one particular type of learning or one particular culture or anything like that. Because I know, for instance, that like the United States has a lot of standardized testing. Anybody who creates standardized testing is going to find that American students do all right with standardized testing because they don't even necessarily have to do the problem correctly. They just have to know how to take the test. And that's not great. Hmm. Hmm. Yeah, and standardized testing is always horrible. Um, I don't I don't want to ever do it. I don't ever want to subject my students to it. But like the end of the year comes, and what do I have to do? I have to give a standardized final to everybody. Yeah, it's pretty rough. Um, I'd say that probably a lot of the like, how can we lose? You know what? Yeah. How are the kids in your school in terms of like motivation to do the work? Do they get like decent grades more or less across the board, or they like just is math almost always terrible, or hmm. I mean that somehow knows things. Honestly, that probably described me pretty well to some of my um, peers in high school. Yeah. So I mean, I think motivation might have something to do with it because if you're like if all the rest of the students in your school are like, "Meh, I don't care. I'm not doing anything," then that's possible that they're just like, they're not gonna do it. So you give them a standardized test that's supposed to rank like Romania versus anybody else, and how many people are gonna fail that? Well, you can, you just have to try harder. Practice is the name of the game, unfortunately. One of the other things to do is you take a ball and you just throw it kind of in their direction, and when they catch it, you go, "Congratulations, you've just done multi-dimensional calculus." Like, our brains are wired for multi-dimensional calculus. It's just that we don't necessarily think about it or do the meta level thinking. That's what these classes are all for, is trying to figure out like the deeper level behind it. Yeah, I find that those students tend to burn out. The valedictorian of the class above us um, was pushed extremely hard by his parents, but also like he started internalizing that onto himself, and like he was going to be a doctor and go to like the go to some extremely high uh, well, I think he was going to Harvard or something like that. And like a year went by, and I went to our state school, just up the road, probably a half hour from where I lived, and I saw him there, and I was like, "Hey, what's going on?" And he's like, "Oh, well, uh, one, he came out, and like that took so much pressure off of him because in high school he wasn't allowed to be gay. And then in college it was just like, oh, people are like me. And I was I was like, hey man, good job, realizing who you are. All right, 1 second here. Now, so anyway, yeah, he yeah, I'm not sure exactly what it was with his parents because I think that they weren't particularly religious, but anyway, yeah, so he came out. He didn't go to Harvard. He ended up just coming back to our state school and switched his major from pre-med to music, and ended up becoming like some insanely great musician. I mean, he already was a really good musician, just in our band. He did like oboe, I think. Um, and then when he went to our university, he ended up doing like oboe and I think a couple of other instruments like on the side. And ended up, I can't even remember where he ended up, but like I think he played with the like some high level orchestra that was pretty close by. So I mean, he found out what made him happy, and it was just like, there you go, man. Like being allowed to be you was really the problem, the thing that was holding him back in high school. Like at one point, he said that I'm sure I have to be careful with this, but at one point he had said that he was going to during his valedictorian speech, uh, commit a mass murder. And I was like, dude, you no, you're under so much pressure. Like, this is obviously hurting you. You need help. Like, you need somebody to talk to that can understand this, because this is not healthy. And I mean, he was already, getting help, but the, he was just so depressed and so upset and everything during all of high school. And then when he got to college, he was just like, screw everything. I'm going to do what makes me happy. And everything turned out so much nicer. That's something to, hopefully, a message to give to other students. It's just that, you got to find what makes you happy. And, you'll figure out how to make money off of that if you want to. Make it your actual career. Like my father ended up, he was going to be an engineer, I think, and he was in college. He took like the first couple of years of courses, then he was just like, this isn't really working for me. And he switched majors, then eventually he ended up dropping out. My parents had me, and then he went and worked for, retail for a number of years, and then he went and got his customs broker license, so he could do cargo movement, and he made a fair bit of money anyway, doing doing that. But by the time he hit 40, he was like, "This is going to kill me. I am miserable. I hate my job. I hate everything about it." With the exception of like some of his coworkers were great. And so, same thing with him. Like, he figured out that he wanted to be a pilot full time. So how can I be a pilot full time? Well, in order to be a pilot full time, I would need to like get all of my ratings up through commercial licenses. Commercial licenses are like 6 levels up and several hundreds of thousands of dollars, or maybe like $100,000 beyond what he had already gotten, which was a private pilot's license. So then how do you do that? Well, he ended up getting all of his licenses all the way up through multi-engine instrument instructor, and ended up doing ended up becoming an instructor. So he was a flight instructor for like 10 years, and he was just like, this is amazing. He loved his job pretty much every day, with the exception of when the airfield was closed due to ice. And then eventually he got his airline transport pilot, which is the top rating that you could possibly get, and that was like another ridiculous amount of money, but that was what he wanted to do. He ended up going and flying down in the Caribbean for years. So he was doing some great stuff. He loved it every single day. He was flying. Flying made him happy. Yeah, go for it with the math list. What else you want to add? Yeah, being good at your job and liking your job are two different things. And it is really, Yeah, it was a shame that like um, it was a shame that my father like was was really good at a job that he hated absolutely, and eventually just decided screw it. Right. So statistics is also. You know what? I did statistics here in my junior year, which was a math majors course. Unlike the uh, 100, yeah, unlike the 100 level statistics, which is here. There's one that's here for non-majors, and this one is here for majors. So then stats usually leads to like combinatorics. And then my master's level had calc based statistics, which like I had the option of taking the second class of this, and I was like, nope, no, 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 no. I took this route, and I was very happy with it. Yeah, we did with our stat course here. We did probably StatCrunch or one of the other programs that was very similar to it, and it was okay, I guess. I kind of wish that we did do stuff in like R or C++, or well, I guess at that time it was C. There was either C++ existed. I know that much. Um, but it was like kind of expensive. So we just had like a C programming class. That was an interesting one. Um, I was actually pretty good with TI programming, like doing the Texas Instrument stuff, input output. Um, and it was okay. So C wasn't that much of a leap, but having to compile your code every day was just like, I really wish Python were around at that time. Because I can run Python in here, and it's just so much faster and so much easier. Don't have to compile stuff, or rather, it's internal, so I don't notice it working. Let's see. Yeah, I liked our combinatorics class a lot. It was also taught by a very southern gentleman. Which one's ML? I've linked this many times before, but I'm going to throw this one in because this is fun. So the Xena project is basically trying to teach computers how to start with the very basics of math and then go. Um, there is a section on there called the natural number game, which is how to... yeah, this is the direct link to it. Eventually, their goal is to, like, get the computer to be able to start solving things which are beyond the scope of human ability. It's going to be a while, but it's an exciting prospect. Is like, wait, the computer might be able to prove new things. Well, this is something that I've been doing for a few months, and I was just like, oh, I'm going to need to do this. Oh, looks like... it looks like it ate all of my previous work, so that's fun. Um, oh well. Alright, anyway. I think probably going to get going here. But... so they are using... what is this? They're using lean. And specifically the lean prover is the thing that verifies math proofs. The lean language is pretty intuitive in terms of mathematics. Yes, it is free. There is a GitHub that allows you to find the prover itself. I don't necessarily recommend using the prover until you have, like, done a bunch of the natural number game, just so that you kind of get how it works. There's also a... is it Slack? It's not Slack. What is it? Zulip. They have a Zulip. I mean, it's like a message board / chat utility. I had never heard of it before I went there, and so they're doing stuff which is well beyond the scope of where I'm at. Yes, so what you do is you alter the code. Yes. So you have to alter the code such that it will prove the line above it. So if you go to like 1.1 or whatever it is, you know, the very first thing at the very top. So tutorial world. So read all that, and then when you get to the bottom, in place of, that was what it was, in place of sorry, you replace it with your code. In the first tutorial world level, that's just reflexive, comma. And once you do that, it proves it using the reflexive property. So literally coming from, you know, the tautology A equals A, you're then going to start building the whole rest of mathematics on top of it. So this is one of the aspects of abstract algebra that I really liked. It really frustrated me to no end sometimes, but it was a lot of fun. And to go back to it now, yes. Yeah, when it says proof complete, you are done. And then you just move on to the next world, or next level. And when you complete all of the levels in a world, you then move on to the next world. At some point you split into addition and multiplication, and you can do either of them in either order. Oh no, multiplication and function. Right, so you get tutorial, addition, multiplication, function. And you can do them in either order. Eventually they merge back. If you don't know what's going on in one of them, you might want to switch over to the other and see if you can kind of like prove stuff between the two and say like, okay, using this other thing, I can do this other thing. In theory, they should not be like based on each other because they are in fact separate paths that you do not necessarily have to go on one to get the other until they merge again. But I don't know. All right. So, hope you have a good week, good night, all that good stuff. And I'm going to, let's see. Jason's still on, so oh, yeah, there will definitely be a day, not necessarily on this channel, but yeah, in some sort of, we will definitely or those people, right? The people using lean will definitely end up proving calculus like all the way through. I think they've done a whole bunch of it. If you check the Zulip, they'll check the Zulip. They're on there. All right, so let's go to see Jason Charles Miller, and we'll. All right, we'll have some music, good times, and hope to see you all, everybody else out there too. Hope to see you all on Friday for more control, and again next Wednesday for more math stuff. So any additional stuff that I have beyond that is just going to be lucky. So we'll see how it goes. All right, have a good night. This is Obi-Wan Pez for N Simplex Pachinko. Good night.